All right. So for hybridization, I think I went a little nuts on this because I want to explain things and I don't understand why we ask you something that you shouldn't understand. But at the end of the day, all you need to know about hybridization is the hybridization of a certain shape. So if there's two areas of electrons, two electron domains is what we would call that, then it's sp hybridized. If there's three electron domains, then it's sp2 hybridized. Like this is straight up like make it on a chart, and this is all we would ask you about it. If there's four areas of um, electron domains, so north, south, east, and west are all occupied by electrons, and that is true for all three of these shapes. Tetrahedral, trigonal pyramid, and bent all have four electron domains around the center atom. These would all be sp3 hybridized. So sp2 hybridized has only two electron domains around the center atom. Sp hybridized has two electron domains. Sp2 hybridized has three electron domains around the center atom, and we're only talking about the center atom. Sp3 hybridization has four electron domains around the center atom, and then, whoops, this I thought there was the next one. So then, if it has five electron domains around it, so if you're looking at, this should be better organized, which it will be. If you have five electron domains, like the crazy shapes, where are the crazy shapes? Here, these two. Okay. So five electron domains around it. So trigonal bipyramid would be sp3d2, d1, or just d, sp3d hybridized, and six electron domains around the center atom. So something that's octahedral would be sp3d2. So that's all you need to know. If you want me to try to explain it further, I'm going to try to explain it here. But that's basically what this is trying to tell you is, right, the number of electron domains. 2 is sp, 3 is sp2, 4, so tetrahedral, trigonal, pyramid, and bent sp3 hybridized. Trigonal biplanar uh, with 5 electron domains around the center atom is sp3d. And octahedral, which is 6 electron domains around the center atom, is sp3d2. Okay, so to explain that, what I kind of was showing you is, and you don't have to listen to any of this anymore. The rest of this is not on the test. This is just to explain it. Mathematically, the shape of the S and the shape of the P's are such that the S is a circle and the P's are dumbbells on the X, Y, and Z coordinates. So if you need things to be a 109-degree angle away from each other in a tetrahedral fashion, right? A tetrahedral being a situation like this, or as we talked about, if your hands are in the air and you rotate your torso so that your feet are coming out and back, right? That is a tetrahedral shape. If you're in a tetrahedral shape, I'm looking for a good tetrahedral. I guess I don't have one local. Um, it's not going to use X, Y, and Z, which are all 90-degree angles. So the people who care about such things had to come up with a reason how these things can somehow become something that allows them to be at 109-degree angles and not 90-degree angles. So they invented this thing called hybridization or whatever. They discovered it maybe, where they take all these orbitals and they put them in sort of this hybridization machine, and it spits out orbitals that are now able to orient at 109 degrees away from each other in a tetrahedral fashion. So that is why this is. And then the reason why you can have five and six things around, it's like at Thanksgiving when you don't have enough room at your table and so many people are coming and you need to make more room at the table and you go and grab another card table and set it up next to your dining room table. Um, that's what the atom does. So here you have phosphorus in its ground state is 3s2, 3p3. If it wants to have five things around it, it now needs to get the card table in the 3D subshell and grab one of those orbitals. And now it can have space for something to come in in the s, all three p's, and the d. So we say it takes all of those orbitals, puts them into the fix-it machine, and it hybridizes them into sp3d so that they're all equivalent and they each have one electron. And the same thing happens with an octahedral, that it would have an sp3d2 because it would need six spaces. So sulfur, which is 3s2, 3p4, would take two of these card tables and move the paired electrons in there so that they had six places available for bonding to occur. All right. And then to explain this further, boron, because it has three electron domains in it, is sp2 hybridized, which means 1p is empty. And that 1p that's empty comes into play later when we talk about acids and bases, because it still wants electrons and it'll go hover around something that has a lone pair of electrons, and sort of mooch off of those. And that's why boron's considered an acid. Again, not anything you need to know for this test. We'll talk about that later. And then another little interesting thing, so long as we're talking about this, carbon and oxygen are sp2 hybridized when they have a double bond. And that's because three of the bonds need to be made. There's three electron domains around the carbon when it's double bonded to an oxygen. So it has a bond with a hydrogen here, a bond with a hydrogen here, and then a bond with the oxygen. And then the double bond forms from the oxygen and the carbon having one electron left in their p orbitals. So instead of this being empty, it would be have one electron in, and then they would sort of overlap with each other and form a double bond above and below the surface of this bond. So here, you can see it, right? So this carbon has three electron domains around it. That's the sp2 hybridization. And then that lonely p that's sitting right up. Oxygen has three electron domains around it, the lone pair, and the bonding. So that's the sp2 hybridization. It also has a p up and down, and then those overlap to form what we call a pi bond. Nothing you need to know, but so long as we're banging on that door, I thought I'd bring it up. All right. Not the best thing, but it'll get you through the test.